In this video, in order to set the stage for later lectures that go into detail, we'll see some basics of neural networks, define some nomenclature, and see how information flows in fully connected neural networks and which types of computations are done in them. Let's dive right in. Basics of neural networks. First, I would like to mention that there are actually different canonical ways of depicting neural network models. First, with information flowing from inputs at the bottom to outputs at the top. Second, with information flowing from left to right. And third, slightly less common, with information flowing from the top to the bottom. Actually, the last couple of layers are also sometimes referred to as the head, and the first couple of layers are sometimes referred to as the stem of the neural network. And with that nomenclature, it of course makes sense to use this leftmost way of drawing the neural network from bottom to top, where the stem is actually at the bottom and the head is at the top. Now, neural networks have different types of layers. They have an input layer, then they have a set of hidden layers, and they have the output layer. The input layer is responsible for representing the inputs. For example, in an image, we typically have 3 different color channels, red, green, and blue, and each of these can be represented by a number between 0 and 256. Those are the numbers that go into this input layer, and they're potentially normalized. Then we have the hidden layers, which are hidden from the observer. So for example, if you observe a human, you can't see inside of their brain. You can maybe see what the inputs are, and the outputs are actions, so you could potentially also see those. But the hidden layers, they're unobserved, and that's why they're called hidden. The output layer, finally, typically represents a probability distribution over the classes, for example, the class of an image. So in order to see what computations are done in a neural network, let's first look at the computations that happen in a single neuron. And there are actually 2 simple steps of computation. So the first one is to take the activations from the previous layer. Each of them is multiplied by a corresponding weight. And then you take the weighted sum of these inputs. The second step is then to perform a nonlinear transformation of this weighted sum. It's important that this transformation is nonlinear because this weighted sum here, well, that's actually a linear operation. And if we only had linear operations like this, we could use as many neurons as we want. We could have very wide layers, very deep layers. We could have parallel computation of different neurons and so on. Still, if each of them only computes a linear function, then well, this combination of linear functions would still be a linear function, and we wouldn't actually be able to express a nonlinear function. But if we have a nonlinear transformation here, and a really simple nonlinear transformation suffices, then we can actually deal with really complex nonlinear functions that we can express and learn. So now that we've seen the computation that happens in a single neuron, let's see the information flow and how the computation is done in a simple, fully connected neural network. So in this particular example, we'll have an input that is a picture. And yeah, by the way, the information flow is here from left to right. So the input is on the left. So the input here is a raw image. And then the first step is to actually feed the pixel values of this into the input layer here. These pixel values are just numbers, and these numbers are then multiplied by this set of weights here, and this happens in parallel to compute the activations in this next layer here. Well, and we apply this nonlinearity in this layer, and then for each of these individual neurons, this activation is then multiplied by the set of the next weights in order to compute the activations of the following layers, and so on and so forth until we arrive at the output layer. And this output layer typically represents a probability distribution over the possible classes, depicted here. So that was a forward pass for making predictions for an individual image given the fixed set of weights between these different layers. What we'll see in one of the later lectures is that we also want to optimize these individual weights by a procedure called gradient descent. And for that, we want to actually compute the gradients of an overall loss function. And this loss function that takes this probabilistic classification and compares it to the true label of the image. And then we take derivatives of this loss function that judges how similar our classification is to the true label, and work backwards to actually compute gradients of this loss function. And so this computation of the gradients, that works backwards, and so that's why it's also called the backward pass. This flows backward to the type of weight that we want to compute the gradient with respect to. So let's say we want to compute the gradient with respect to this weight, then we need to flow this backwards pass up to this point here, where we have then computed the gradient with respect to this weight. And well, if we only want the gradient with respect to this weight, we could stop here, but typically we want to actually compute the gradients with respect to all of our weights. So we flow this information backwards to compute it for all of the weights in the neural network. And then we can take these resulting gradients and pass them to an optimizer that then does, well, stochastic gradient steps to optimize these weights in order to minimize this loss function. All right, so summarizing, we have the forward pass flowing from the inputs to the outputs to compute our probabilistic predictions. And we have the backward pass flowing backwards to compute gradients of the loss function with respect to any of the weights. So this brings us to the end of the video, and I'd like to leave you with these questions to think about for yourself. And I thank you, and I'll see you in the next video.